653 which followed an 85.
Look carefully at this picture. Notice anything strange? Come on, I'll give you 5 seconds. Well, look at this angle right here between this horizontal line and the Javelin. It is exactly 45 degrees. Coincidence?
95. He really is getting confident and hammers that one out, but it's not. Oh!
Let's look at another clip. 45 degrees here and here again. What's going on here? Why are all of these angles 45 degrees? This isn't just a Javelin thing. This 45-degree angle can be seen all over the place in football, basketball. So there must be a reason to it. Let's say you're kicking a ball and you want it to travel as far as possible. What angle should the direction of your kick make with the ground? Answering this problem is the key to our video here. Well, let's call it X for now. Let's draw the X-axis here and the Y-axis up here. When you're kicking the ball, you're essentially giving it an initial velocity, say v0. A quick tip: whenever you see something in motion, you should immediately think of Newton's second law, which says that the sum of the forces applied to this ball is equal to its mass times its acceleration. What forces do we have in our case here? Well, when the ball is in the air, there's only one force, which is the weight of the ball, commonly denoted by W. It is equal to m times g, g being the acceleration due to gravity. Canceling m, on both sides, we see that the acceleration of the ball is exactly g. The x component of the vector w is just 0, so ax, the x component of the ball's acceleration, is 0. That means vx, the x component of the velocity, is a constant, which is the x component of the initial velocity, v0x. Finally, x of t, the distance traveled by the ball in the x-axis at time t, is equal to v0x times t, plus x0, the initial distance, which in this case is just 0. Now we got our formula for x of t. Similarly, we can derive the formula for y of t. It's minus 1/2 g times t squared, plus v0y times t plus y0. Again, y0 is just 0, so we'll ignore it. Let's go back to our graph one more time. The vector v0 is right here, tangent to the trajectory. Its component, v0y, is this, and this is the angle x. Sine of x is v0y divided by v0, so v0y is v0 times sine of x. We're done with the two formulas. Now we want to determine the coordinate of this point, the point where the ball is going to hit the ground. Well, this point is where the curve crosses the x-axis, so we must have y of t equal to 0 right there. Let's write the formula like t times minus 1/2 g times t plus v0 times sine x. Obviously, t isn't 0, so this thing right here should be 0. This is the time where the ball is going to hit the ground. Now, to get this distance, we should plug this value to x at t. Substituting, we get 2v0 over g times sine x times cosine x. Okay, we're almost done here. Our goal is to maximize this distance here, which we have shown is equal to this. Notice how sine x times cosine x controls this expression. The bigger its value, the bigger the distance. The function sine x times cosine x has a maximum at x equals pi over 4, or 45 degrees. So the angle you should kick that ball at is exactly 45 degrees. And this brings us back to the start of the video, throwing the javelin, kicking a football, or shooting a basketball this far out. The goal of all of these activities is to get the ball as far as physically possible, and that's why these angles were 45 degrees.